All right, so in these notes, we're going to go over our packet that is about, it's a library of parent functions, so that you can see what the different parent functions are and what their transformations are. So if you look, I gave you kind of like a menu of the different transformations that we have listed here on the front page, and you can see that I did those with a general function. I'm calling that, sorry, change this to a color. I'm calling that f of x as that original function. So you can see that the inside of the function is in there with the x part. The outside of the function is this a in the front and this k on the end. So if you guys recall, there are different transformations that we have. If you have a coefficient in the front, that number tells you if you have a stretch or a compression, or if the graph has been reflected over the x-axis. So remember, stretches would be numbers like 3/2 or -5/4 or 1.2 or -7, something like that. A compression would be a number that's absolute value is smaller than 1, so that'd be like 2/3 or -0.4 or something like that. Any negative number, it doesn't say anything about a stretch or compression, it just tells you that it's been reflected over the x-axis. The c values that you can see inside the function, but kind of like outside those parentheses, that's a transformation that is new to pre-calc, so we have not looked at that yet. We'll do that in a few days. The number inside these parentheses, all the way inside the function, if it's a subtraction sign, so you're minusing something, then it means you've shifted to the right. If you're adding something, you've shifted to the left. And then the number on the end tells you if you've shifted up or down. So we're going to look at those. Hopefully that is review. So the first parent function we're going to look at is the absolute value parent function. You can see how it looks with all those transformations inside the equation right there. So with the absolute value function, we always start at the vertex 0, 0, and then from the vertex 0, 0, you go to the right one, up one, to the right one, up one, to the right one, up one. From the vertex to the left, we go left one, up one, left one, up one, left one, up one. So that pattern is going to be important because it's going to help us graph a transformed absolute value graph. So we're going to go ahead and look at number 1 first, and it's going to be helpful if we identify what our transformations are. So that negative in the front tells you that the graph has been reflected over x. And then the 2 in the front tells you that the graph has been vertically stretched by 2. The -3 inside the absolute value sign kind of tells you the opposite of what you would think. So it tells you that it goes to the right. 2. Oh, that's a 2. And then the number on the end, that +1, tells you that it goes up 1. I'm sorry, I'm kind of not great with the stylus. I'll get better, I promise. Okay, so if the original vertex happens at 0, 0, that's like normal, and we've shifted to the right 2 and up 1, then that means that our new vertex is going to be at the point 2, 1. So I'm going to go ahead and zoom in so I can graph that easily. So 2, 1, there we go. And then from there, the graph is going to be upside down. I know that because it's been reflected over the x-axis, and it's been stretched by 2, so it's going to grow twice as fast as it normally does. So instead of going over 1, up 1, it's going to go over 1, down. And instead of going up 1, we're going to take those up movements and we're going to multiply them by 2 because we're stretching this graph out. So I'm going to go to the right 1, down 2, to the right 1, down 2, to the right 1, down 2. And then the same thing to the left. So you can see that the effect that it had on my graph is not only did I flip it upside down, but it stretched, that was almost good, it stretched vertically, so it grew twice as fast as it normally would. Okay, so there is our transformed absolute value graph. And for today, we are only going to focus on the odd numbers in the problems because I wrote the even numbers to be used later. Okay, The next parent function that we're going to look at is a quadratic. So again, you can see that the locator point is at 0, 0. So, and we're going to call it a vertex. And then quadratics grow in a different way. They go over 1, up 1 first, and then they go over 1, up 3, and then they go over 1, up 5. So over 1, up 1, over 1, up 3, over 1, up 5. The pattern continues, then it would be over 1, up 7, over 1, up 9, over 1, up 11. So that's the pattern there for how they grow. So let's go down here. So here we have a few transformations again. We have a vertical compression, and the compression is 1/2. So it's going to grow half as fast as it normally does. We have the +4 in there, so that means that we have moved to the left 4. Ooh, that 4 looks terrible. There we go. And then we have a -7, so that means we have moved down 7. You guys, I promise I'll get better. Oh, so bad. Okay. So if the original vertex is at the point 0, 0, then our new vertex moves to the left 4 and down 7. So our new vertex is at the point -4, -7. So I'm going to go ahead and plot that point, -4, -7. There we go. Okay. And we're going to grow half as fast as we normally do. So it normally goes over 1, up 1, over 1, up 3, over 1, up 5. So we're going to go over 1 and then up half of 1, which is just a half. And then, instead of going up 3, we're going to go up half of 3, which is 1.5. So over 1, up 1.5. And then instead of going over 1, up 5, we're going to go over 1, up half of 5, which is 2.5. And then instead of going over 1, up 7, we're going to go up half of 7, which is 3.5. You don't have to do all these points, but I just wanted you guys to see like how it works. Kind of squiggly. Okay, so that's what your paper should look like. All right, now before we go too much further, I forgot to find the domain and the range for the first problem. So let's go ahead and go back and do the domain and range. So if you guys recall, the domain is just whatever your possible x values are that you're allowed to plug into the function. And you can see that I wrote here that the domain is all real numbers. It's from -infinity to +infinity for the absolute value graph. And the reason for that is because you can plug any x value into an absolute value. Any number you want. Negative numbers, decimals, fractions, anything you want can always be plugged into an absolute value graph. And so that means that no matter what we do to it, the domain of this is always going to be -infinity to +infinity. Always, always, always. Now the range is different. The range is like what you get for your y values when you plug those x values in. And you can see that for the range, I already gave you kind of a hint as to what our range should look like. So in this graph, we're going to look from down to up. I can see that the bottom, I'm going to choose a different color. I can see the bottom of the graph is arrows, so that's -infinity. The bottom of the graph goes down forever, so all of those negative numbers are being used. I can see that the top of the graph is the vertex. So that means that my range is going to be the second option here. So it's from -infinity up to the vertex, and when I write it, I want to make sure that I'm writing it using the y coordinate because this is the range. So it'd be -infinity. Oh my gosh, that's so hard to write. I'm going to zoom in. -infinity to, and then the y coordinate of the vertex is 1. So -infinity to 1, and I put a bracket around the 1 because that's the number that actually shows up on the graph. Okay, let's go ahead and look at the quadratic example that we had. So again, with the quadratic, you can see that the domain is -infinity to +infinity, and that's because there's no limit to the number of x values that you have that you can square. I can multiply anything by itself. That's all it means when I square it. And so my domain for this problem is just going to be all real numbers. No reason for it to be limited. But just like the absolute value graph, our range is going to be a little bit limited because when you square something, you force it to become positive. So that means there are going to be some y values that are more limited when we plug in those x values. So here, again, I gave you a hint about what the range should look like. So it's definitely based off of the vertex. And if you look at our picture, you can see that the very bottom of the graph happens at the vertex, and the very top of the graph goes to infinity. Right there, it's got arrows that go up. So that means that on here, we're looking at the first option from the vertex up to infinity. And we're going to use the y-coordinate of the vertex, which is -7. So our range is from -7 to infinity. Okay. Let's go ahead and look at the next one. So for the square root function, this time we can't call it a vertex. It's definitely going to be called a locator point. And this one has an interesting growth pattern. Goes right 1 up 1, right 1 up 1, right 3 up 1, right 5 up 1, right 7 up 1. So it always goes up the same amount. You'll notice it's very similar to the x squared graph. It's just going right that much instead of up. So right 1 up 1, right 3 up 1, right 5 up 1. So it definitely, it's like a parabola. It's been flipped on its side. All right, so here, again, we've got some transformations we're going to work with. We have a vertical compression. Oh my goodness, you guys. This is so difficult. Vertical compression of 2/3, okay? And then the +5 on the end tells us that it's been shifted up 5. Okay, so our original locator point was at 0, 0, but our graph has been shifted up 5, so we're not going to graph that 0, 0. Our locator point is going to be at 0, 5 this time. So 0, 5, there we go. And then the normal pattern says up 1, or over 1, up 1, over 3, up 1, but we're only going to grow by 2/3. So we're going to go over 1, up 2/3, over 3, up 2/3, over 5, up 2/3. And that's what our graph is going to look like. Okay? So it didn't go up very fast because it was only growing by 2/3. Okay, and then for this one, we'll notice that for the domain, we definitely have a limited domain because there is a limited number of x values that you can plug into a square root sign. So when we look at this, we can see that the domain is going to be dependent on our locator point. So here, we know that the furthest to the left the graph goes is 0, right? Like the graph doesn't go past that to the left. And then to the right, it goes on forever. So it goes from the locator point to infinity is what it does. So if you think about the equation that we're using, this one right here, the very smallest value of x that you can plug in is 0. The square root of 0 is just 0, so that one's okay. But you can't plug in -1. You can't plug in -2. So here for our domain, we're going to write that the domain of this graph is from 0, and I'm including it, I can plug that in, and then all the positive numbers work. So from 0 to infinity, our domain is just fine. All right. The range is going to be, again, those y values that show up as a result of the x values that you were able to plug in. And for the range, we'll notice that the bottom of the picture is this part right here. And then it goes up rather slowly, but it does go up forever. It's got an arrow, so it goes up forever, just very, very, very slowly. So for us, we're going to say the range is that y-coordinate. So the range is the lowest y value, which is 5, and then it goes up forever, so that would be infinity.